Hello everyone, I am honored to take part in Visita World Congress 2023 in Barcelona. My name is Mohammed Hariri and I will be presenting the findings of my research. The research that's leading to the completion of my doctorate study, and it's mainly directly linked to the safety of the battery packs in electric vehicles. And to be more specific, it's a finite element analysis in trying to predict the kinematics and the dynamics of the battery packs in electric vehicles when the car is involved in in medium to high speed full frontal collision with a rigid barrier. In this presentation, I will start with brief introduction covering a little bit of history relevant to the electric vehicles in general, and then moving forward to the challenge that we have with electric vehicles nowadays, and to be more specific, the challenge associated with the use of the NCA, the nickel cobalt aluminum lithium ion batteries in the battery cells. And then we will also cover the different type of abuses the battery pack can be exposed to. Then we will have a look into what we know so far, which forms the foundation of my research actually, and then we will see the finite element model that I developed for that purpose, or for this purpose, to study the safety of the battery pack, and then we will end with the analysis and presenting the results. There have been different types of engines since the early days of the invention of cars, whether it's the steam engines, internal combustion engines, or even the electric engines. That even before way before the beginning of the 20th century. And what most people maybe don't know is that in the early years of the 20th century, there were dozens of electric cars driven in the streets of London and streets of New York. Battery cells, widely or commonly used in battery packs in the electric vehicles nowadays, is the nickel cobalt aluminum NCA lithium ion batteries. And we can see here the main ingredients, the different sheets in the rule within each and every cylindrical battery. My study is mainly focused on where the two red boxes are highlighted, where when we have a mechanical load that might result into reactions of electrode with the electrolyte or damage to the solid electrolyte interface. And they were able to define, if we look in the top chart to the left, we can see that at around between 6,000 and 7,000 Newton, that's where the magnitude of load. And you can see the green light covering the two charts. That's where you can see the associated complete loss of voltage or the short circuits inside the battery cells. To the right, we can see the setup, the method they have used, the machine, and then the type of subject they have used. Similarly, so in this, this is as a function of time, okay? They have presented their work. To the left, we have the load, to the right, displacement. At the lower one, we have voltage, and to the right, we have temperature. In this type, which is the point of short circuiting in lateral rod indentation test. What was amazing as well, similar result registered or recorded, if we go next, in the same test they have conducted, but in a different setup. Here we have the hemispherical punch crush test results. We can see that it's actually below between 5,000 and 6,000 Newton. That's where you can see the green light, the green line, where indicates the occurrence of the internal short circuit event and the complete loss of the voltage. And then we can see the rise in temperature in both of them. So if I go back to the previous one, we can, the lower chart to the left, you can see the red line indicating the temperature, and you can see the moment the battery cells experiences a short circuiting, there is and spike in the rise of in the temperature. But we will see in a second that similarly here. So we have to the left here, if you keep your eye on the blue line, here is the temperature, and it's in the left side, okay, of the chart, the lower one. The blue line in the lower charts, so we have the temperature, and then at the moment of the short circuiting, it experiences a dramatic rise in the temperature. Yet still, below 50, it's still considered to be something that the battery cells can bear. But it's just we lost the voltage. The short circuiting happened at that certain point, and then a complete loss of the voltage. Another interesting and amazing study, and this was actually conducted in one of Sunderland's university labs, called the AMAP. Okay, so if we look at the orange one in the middle, and that is the separator number 5, we can see it has exceeded the melting point. Okay, and what's interesting in this chart, it's not in a time, it's not as a function of time, it's as a function of displacement. So at the bottom, you see in the x-axis, you see the displacement in millimeter. To the right, we have temperature registered, and to the left is the force. So it's a really critical kind of in-depth insight into what's going on to the separators, how they behave under load. Now, taking all of that information in place and collecting the facts that we know and published officially from Tesla and other sources in order to design the finite element structure for the battery pack. To the left, you can see the picture where I used imaging processing software that helped me a lot to estimate the sizes of the internal component of the battery packs. And then in the middle, to the lower, we have the patent structure. And what's interesting here, you can see that the battery pack is located not at, it doesn't go in a perfect alignment to the front end. Okay, so I had two assumptions while I am designing the finite element and model, as we will see in a second. And to the right, we can see the different calculations I made so that I can develop the finite element model of the battery pack. And here were the initial finite element model of the full-scale battery pack. Now, the model was scaled down to 2 modules only, to study the effect of 2 modules for many reasons, but mainly it was for the to reduce the computational time and processing time for the full battery pack. And so we end up, if we look on the left, we'll end up with 2 modules where the battery modules are. And now here are the technical details about the model. Each part, we have the crush boxes, we use the material which is the piecewise linear plasticity. For the front frames, I use the material plastic kinematic. The impact bar, it was the piecewise linear plasticity as well. For the jelly core, within the 444 elements inside the module, I use the material modified crushable foam, and then finally the material for the rigid barrier, which represent the steel. And to the right, we see the dimensions of the meshes. Okay, the material properties assigned to all materials, as we can see in this table. Okay, here we can see the finite element analysis. This is for the failed Model A structure. Okay, That's the it wasn't reliable for the test. Where the battery pack is not in a perfect alignment with the frontal end, as we can see in the top. Okay, and we can see an like an immediate, instantaneous buildup of pressure at the bracket points. Okay, and that because at the moment, that's at the very first instant of the collision. Okay, the impact between the front end and the rigid barrier, the pressure buildup at the brackets area, and that's not wanted actually. Okay, the crush boxes should like an effective one should try to absorb the energy generated from the high speed frontal collision. And at the in the picture B, we can see as a result of that, the huge momentum, the weight of 55 kilogram, estimated about 55 kilogram of the battery pack. Okay, the structure wasn't able to hold it at its location. Okay, and it slid down the structure, and kind of it shoved upwards the structure. Okay, as in real life, how's the case gonna be? But this is not the results that we will be looking for. And we can see to the right the charts of the huge amount of the momentum and the kinetic energy of the system, and we can see that it failed to hold it. I mean, we don't have consistency of results, because again, the battery pack like slid from from underneath the structure. It kept moving until it hits the rigid barrier at 0.1 second, because it's high speed impact. 0.1 second, and that's where it has completely lost its energies, because it came to a complete settled situation when it hits the rigid barrier. In model B, however, we can see the battery pack is located in a perfect alignment with the frontal end. Okay, and you can see here the frontal frames, and then we have I mean, if we start from the battery pack, okay, the pink one, I'm talking about the left picture, followed by the frontal frames, followed by the crush boxes, and then the impact bar. And here we have the isometric view to the right for model B. The results of this impact, it was amazing. Okay, although the initial speed for the simulation compared to a real life experimental data, there was variation. Okay, the real life experimental data, it was for around 16 meters per second, whereas the finite element model, it was at 20. This variation wasn't able to change it, because unfortunately at the time of validating the model there was no access to the finite element solver. But we can clearly see the behavior of if we look at the orange line, that's the experimental results. The red line is the finite element results. We can see that there is a consistency between the behavior of the finite element results and the real life crush. And of course, the variation can be referred to the type of materials used in the model. Now here we have more critical analysis. Let's remember that the main objective, the main goal of the study is to try to predict the amount of energy translated from the frontal impact and reaches the battery pack when the electric car is involved in medium to high speed full frontal collision with a rigid barrier. Okay, so to the left, and by the way, all the results here are function of displacement. The x-axis is displacement. To the left we have chart with the deceleration that compares between the failed structure A, that's the orange color, and the successful structure B in blue color. So the orange curve is for the failed model, the blue curve is for the successful model B structure. Okay, so the deceleration to the left, and we have the velocities recorded in the right. What we can see, the analysis took two stages. Stage one from the displacement point 0 to 360, okay, millimeter, and that applies to all analysis. In addition to those, what we will see in a minute. That's stage one, and then stage two from the point 360 till the end of the simulation, and which means that is the end of simulation was at 0.1 second, 0.1 second. Yeah. So until the end of stage one, we can see that both structures behave in a similar manner, where we can see that it's similar to like a perfect sinusoid, a damped wave, okay, in sinusoidal behavior. So we have a kind of consistency, but after the end of stage one, we can see the structure has already approached the like it behaves in a plastic manner. It's unreservable. It will not be able to recoil its original structure, okay, but then immediately we can see the variation between the structure of model A. Remember, model A, the failed one in orange, the blue curve is model B. That's the huge variation. If we take a look to the right one, okay, because sometimes the deceleration can be a little bit confusing. If you look at the velocities, we can see the blue one, which is the successful structure model B. The velocity dropped till it gets to 0, and it has a recoiled, because the full structure has completely came to 0 velocity after hitting the barrier, and it's as any like objective, any objects in real life, when it collide with any rigid objects, it will recoil, and that's what happened. We can see there was a bit of recoiling in the blue curve, whereas if we look at the velocity of model A, we can see the battery pack or the system has retained its velocity until the battery pack hits the barrier. Here we have the force. Again, remember the x-axis is the displacement. To the left we have the force magnitude, and to the right we have the kinetic energy. We can immediately we can see that the model A, the orange one here, the orange one here is, it's the failed model A curve, and the blue one is the model B. And we can see that in the forces how model A failed to completely dissipate the force, and we can, if we look at the kinetic energy to the right, okay, we can see that model B was able to dissipate the energy at around 50% of the time, okay. It didn't complete the 0.1 second time period where we can see the model A structure wasn't able to get rid of the kinetic energy due to the continuous motion of the battery pack until it hits the barrier. So here we have the amount of forces, and we have the kinetic energies that approaches the battery pack in electric vehicle when it's involved in medium to high speed full frontal collision with rigid barrier. In this chart we see the energies for the whole system. That includes the battery pack, the frontal structures, the crush boxes, the frontal impacts. Okay, that's for round over 140 kilogram. We have the kinetic energy in red and the total energy in green. Yeah, and we can see the total energy. It applies the principle of the energy conservation in physics. Right, so this study has helped to set the foundation. This is for future work to develop a smart structure for the battery pack. The controller required for the smart structure was developed, and we can see the transfer function was put in place, and we can see the like a rough schematic sketch for the imaginary battery pack, how it's gonna look like. Here we have the list of references used in the presentation, and if there is any questions, I'll be honored to discuss any points that was covered in the presentation. Thank you very much for listening, and I can't wait to take part in PhysITA World Congress 2023 in Barcelona. Thank you very much.